Hello and welcome to week 2 of the course Theory of Computation, and this is lecture 6. In week 1 we saw the introduction to the course. We saw deterministic finite automata, DFAs. We saw that the languages recognized by DFAs are called regular languages, and then we saw that we saw some closure properties. We saw that regular languages are closed under complement. And then we saw that regular languages are closed under the union operation, and then we said that there are operations called union, concatenation and star, which are called regular operations, and we said that regular languages are closed under all the regular operations. So the next thing to do was to show that regular languages are closed under the concatenation operation, and we realized that we could not, it was not straightforward to show the same thing by using techniques similar to how we showed the closure under union, right? So basically the model of DFA seemed limiting, right? So towards this end, we said we wanted some other techniques, and that is what we will see in this lecture. So we will see what is called non-deterministic finite automata. It's a model that is similar to DFA but seems to have a bit more powers. Okay, it's called NFA in short. It is non-deterministic finite automata. So the definition is the same. Like instead of deterministic, we have non-deterministic. Okay, so let's see what are the major differences between DFAs and NFAs. Okay, so the major difference is that in a DFA, right? In a DFA, let's say there is it's a binary alphabet, right? So if there is a state S, right, and let's say there are two symbols 0 and 1, binary alphabet, there is an arrow, outgoing arrow for 0 and an outgoing arrow for 1, right? There will be two such arrows, exactly two such arrows for each symbol of the alphabet. It is possible that maybe both the arrows go to the same place, so it could be something like this, right? It's possible that one of the arrows are like one or both of the arrows are a self loop. It's possible that both of the arrows are self loop, but the point is that there is one. So if you are at S and you are 0, you know where to go next. If you are at S, you see a 1, you know where to go next, right? So for any state and for any symbol, you know what exactly is the next step to take, right? This is what makes a DFA deterministic, right? So if you are at a certain state and if you see a certain symbol, you know exactly what the next step is. So the current state and the symbol that you see completely determine where you should go next. This is not the case in NFAs, right? So in an NFA, the thing is that you could have multiple outgoing arrows with the same symbol. So there could be 2 arrows or there could be 3 arrows with the symbol 0, right? There could be no arrows with the symbol 0 as well. It could also be 1. So the number of arrows of a specific symbol from a specific state. So when I say arrows, I mean outgoing arrows. This could be 0, it could be 1, it could be more than 1, right? 0, 1 or more than 1, right? So the consequence is that sometimes there are multiple options available. Sometimes there is no option available. Sometimes there is only one option available. Okay, so this is one of the main differences. The next thing is that in DFAs, all the arrows are labeled with the alphabet symbols, right? So if the alphabet is binary, it is just the arrows are labeled 0 or 1. In the case of NFAs, you could also have arrows marked with epsilon, where epsilon is the empty string. Okay, so this is the empty string. So what this means is that, so if you recall, in a DFA, you read a certain symbol and then you traverse an arrow and make a transition, right? That's what you did in a DFA. In an NFA, if there is a arrow marked with an empty string, okay, you could make the transition, you could traverse the arrow marked with the empty string, but without reading any input symbol. Right, so you could make the transition without reading any input symbol, provided the transition or the path is marked with a empty string, right? So and not just that, you can have 0, 1 or many such arrows marked with empty string. So in from one state you could have multiple arrows marked with epsilon. Okay, right? So this may seem a bit confusing for now, but it's not all that confusing. We'll soon see some examples. Okay. So as I already said, both of these things. So one is that there could be multiple arrows with the same symbol. Then there are these epsilon transitions, right? Which means you can make a transition over an arrow which is marked with epsilon. Both of them result in some options for the NFA. Like in a deterministic finite automata, you look at the next symbol and then you know where to go next, and then you look at the next symbol after that, and then you go somewhere else. So the process is completely deterministic. There is nothing for you to like decide or determine, or there is no choice or options available. In the case of an NFA, the choice, there are choices, there are options available, and this can lead to multiple possible computation paths. So there could be many possible computation paths for the same input string. So we'll see an example. The same input string could have many possible computation paths, right? So let's see an example. Okay, so and one more final point is that an NFA accepts a string if there is a way to process that string such that once you complete processing that string, you end at an accepting state, right? So in this particular NFA that I have drawn, there is only one accepting state, which is Q4. But you accept a string if out of the many possible options, there is at least one way to process the string ending at an accepting path. There could be other ways which do not end at an accepting path, but if there is at least one way to end at an accepting path, you say that the string is accepted by the NFA. So let's see what happens here. So let's consider some simple strings. And let's see whether they are accepted or not. Let's consider the string 111, or let's say 1111. So upon seeing the first one, you could remain at Q1. You could just remain at Q1 throughout. First one, second one, third one, fourth one, right? Which means it's not accepted. But then you have options. Upon seeing the first one, you could you could go to Q2, and then you make the transition. There is an epsilon transition available here. Notice that there is an epsilon transition available. So from Q2 you just make an epsilon transition, which means you don't read the input, right? So you read the first symbol, which was a 1, and then you read then you came to Q2, then you took the epsilon transition to Q3. Okay, so this arrow is marked with 0 as well as epsilon, right? Right. So, and then the second one is used to transition to Q4. So once you are at Q4, there is only one option available, right? So the third one keeps you at Q4, this self loop. Fourth one also keeps you at Q4. So so then you end at Q4. So this is another way to process the same string ending at Q4, which is an accepting state. So that therefore this string is accepted by the NFA above. So notice that this is indeed an NFA, right? It has more flexibilities, right? So Q1 has 2 outgoing arrows marked 1, 1 outgoing arrow marked 0, right? Which is a self loop. Q2 has no outgoing arrow marked 1, right? And Q2 further has an epsilon transition available. Q3 has no outgoing arrow marked 0, right? So if you reach Q3, all right, and the next symbol that you see is a 0, then you don't have a way to go, right? So let's consider another string. Let's say 100. Suppose you take the transition 1, the first symbol takes you to Q2, Suppose you took that option, right? The first symbol could also, you could remain at Q1, but let's say you move to Q2. The second 0, you move to Q3. And now the third 0, there is nothing for you to do because there is no outgoing arrow at Q3, which is marked 0. So then, which means that you are stuck. There is also no epsilon transition. If there was an epsilon transition, you could take the epsilon transition and hope to hope that the next state has a valid transition available, but even that is not there, right? So 1 0 0 does not get accepted in this manner, and if you look at it, it does not get accepted in any other manner as well, right? So you can check this. Is not accepted. So by that, what I mean is there is no way for this NFA to read 100 or process 100 such that it ends at the accepting state. Right? So the way we said, so if you are at a certain state and you don't have a valid outgoing arrow for the corresponding to the next symbol, that means that is not a valid computation path available. Right? So maybe let's say some other string, let's say 1010. Of course, it's always an option to remain at Q1 throughout, but then that is not good enough because that doesn't take you to the accepting state. So 1010, let's say the 1 takes you to Q2, 0 takes you to Q3, 1 takes you to Q4, and then 0 keeps you at Q4, the self loop. So this is accepted, right? Because 101 you move to Q4 and the last 0 you remain at Q4. Notice that this is the only way this could have been accepted. If you chose to remain, or if you chose to remain at Q1 upon reading the first one, then you have to remain at Q1 for the 0 as well, because that is the only outgoing 0 available. Then if you move to Q2 and then you take the 0 transition to Q3, you cannot go to Q4 because there is no further one, right? So the only way to get accepted is to the first one itself you move to Q2, the second symbol which is a 0 you move to Q3, and the third symbol which is a 1 you move to Q4, right? So if you notice, you can remain at Q1 throughout, or you can remain at Q4 throughout. The only way, there are two possible ways to move from Q1 to Q4. One is that you have 101 somewhere in the middle of your string, which is what happened in the string here. There is 101 at the beginning. The other possibility is that instead of the 0, you could use the epsilon transition to move from Q2 to Q3, which means you should have 1 1, the string 1 1 somewhere in your, the substring 1 1 somewhere in your string. Only then could you go from Q1 to Q4. So the language that is accepted here is the set of all binary strings where W contains 101 or 11 as a substring, right? So unless 101 or 11 is there as a substring, which means in that order continuously without anything in between, you are not going to get accepted. So this, you can try working out this and see that this is indeed the case. So this is the idea of non-determinism. So you see how even the same string presents us with multiple options, and you accept if any of the valid computations lead to accept. Non-determinism can sometimes be thought of as guessing. So there are multiple options available, and the machine is able to guess the correct computation, right? So now let's see another way to kind of see whether this computation or this machine captures this machine is able to accept a certain string or not. So the string is that I have written here bit by bit, 0 1 0 1 1 0. Okay, so string is 0 1 0. I'll write here 0 1 0 1 1 0. Okay. So it is the same NFA that is written over here. I have just shrunk it and reproduced it here because I need space over the right side. So the first 0 keeps you at Q1 because Q1 has only one outgoing arrow with 0 on it, right? The second one, the second symbol 1, there are three options. You are at Q1. So if you are at Q1, one is to take the self loop and remain at Q1, right? Other one is to take the outgoing arrow to Q2. If you take the outgoing arrow and go to Q2, you could also take the epsilon transition available to go to Q3. So one is that you remain at Q1, or you go to Q2, or you go to Q2 and then take the epsilon transition, right? So these are the three things that you can do upon reading the second one, right? Now there are three possibilities after reading 0, 1. You are at Q1, Q2 or Q3. Third symbol is 0. If you are at Q1, when you see a 0, you remain at Q1. That is the only option. If you are at Q2 and then you see a 0, you can move to Q3 using the Q2 to Q3 arrow. If you were at, so I am referring to this, the third transition, the second transition here, okay. If you are at Q3 and then see a 0, there is no outgoing arrow available. So which means there is no, this path gets stuck. There is no path here, right? No option available. No transition available upon seeing a 0 from Q3. Right? So the Q3 has only one outgoing arrow, which is a 1. So now after reading 0, 1, 0, you could be at Q1, right? Or you could be at Q3. These are the two places where you could be. Now let's see what happens next. The next symbol is 1. If you are at Q1 and see 1, we already saw it in the second step. There are three possibilities. Either you take the self loop, remain at Q1, or take the Q1 to Q2 arrow and then go to Q2, or you take the Q1 to Q2 transition and then take the epsilon transition, which means there are three possibilities, which is Q1, Q2 or Q3, right? This you saw in the second step as well. If you are at Q3 and see a 1, then you reach Q4, right? Which is what we get here. So now after seeing 0, 1, 0, 1, all four states are possible: Q1, Q2, Q3 or Q4. Now the next symbol is again 1. If you are at Q1, there are again three possibilities, right? Q1, Q2, Q3 upon seeing a 1. If you are at Q2 and see a 1, there is no possibility, right? So this path gets stuck. If you are at Q3 and see a 1, you can go to Q4. If you are at Q4 and see a 1, there is self loop available. So again Q1, Q2, Q3, Q4, all possibilities are available after seeing 0, 1, 0, 1, 1. But Q4, there are two ways to reach Q4. The others you can only reach one way: Q1, Q2, Q3. And finally, upon seeing a 0, from Q1 you remain at Q1, Q2 you can go to Q3. Q3 there is no outgoing arrow. Q4 you can remain at Q4 using the self loop. So there are four possibilities. In fact, three possibilities: Q1, Q3 and Q4 upon seeing the string 0, 1, 0, 1, 1, 0. But the three possibilities, but then there are two ways to reach Q4. One is to the 0 keeps you at Q1, then you move to Q2 upon seeing a 1, then you move to Q3 upon seeing a 0, then you move to Q4 upon seeing a 1, right? So so what happens in the first case is that this 1, 0, 1 takes you to Q4 and then you remain at Q4. The second case is when 0, 1, 0, 1, 1, 0. The second case is you remain at Q1 till you reach 0, 1, 0. Then you move to Q3 upon seeing the fourth symbol, that is a 1. So Q1 to Q2 and then the epsilon transition. And then you move to Q4 upon seeing the fifth symbol, which is a 1. So this 1, 1 takes you to the accepting state. So there are two ways to read the string and accept, right? So again, this tree, we call it the computation tree. It captures the two different ways the string could be processed, or no, many different ways this string could be processed. In fact, there are four valid ways. of completely processing it, and 2 of them need to accept. So which means this string will be accepted. So you don't need 2, you just need 1 to be accepted. Okay. So 010110 is accepted by this NFA, and this is consistent with what we wrote above. It contains 010 or 11 as a substring. It in fact contains both. Right. So this is what NFAs are. Right. So and this computation tree captures everything possible. So right. So the thing is, it must be clear now that NFAs are at least as powerful as DFAs. Right, because the things that we all said, right, there are 2 things that we said. One is that there are 3 things in fact. One is that you could have multiple outgoing arrows or 0 outgoing arrows, and then the second thing is that there could be epsilon transitions, which transition on an empty string, and the third thing that we said is that you accept if there is at least one way to accept. So one point is that NFAs, anything that you can do with a DFA, you can do with an NFA, because the DFA itself is an NFA, right? So regarding point 1, so we already say that 0, 1 or more than 1 is possible. So 1 is a possibility. So DFA is an NFA where every time there is exactly one outgoing arrow, right? And the epsilon transition we just refuse to use in an NFA, then we get a DFA, right? So anything that can be done with a DFA can be done with a NFA. So NFAs are at least as powerful as DFAs, because DFA itself is an NFA, but we may be able to do the computation using smaller number of states, using a smaller number of states. Okay. So a natural question here is that are NFAs more powerful? Is there something that an NFA can do but a DFA cannot do? The answer is that no. Everything that an NFA can do, you can write a DFA for the same thing. Just that you can perhaps get a simpler NFA for it. So what that means is that NFAs, even though it seems to be more powerful, the class of languages recognized by NFAs are exactly the same as the class of languages recognized by DFAs, right? So we'll soon see that. So we already said that anything that you can do with a DFA can be done with an NFA, which is straightforward. You don't need a proof. But we'll also see that anything that can be done with an NFA, you can write a DFA for it. So this may be a bigger DFA, more involved DFA, but it doesn't matter. It's a finite state machine, so it will be a DFA. So we'll see later that NFAs and DFAs are kind of equivalent in power, in the sense that if you don't bother about the number of states, etc., anything that an NFA can do, a DFA can also do, and vice versa. So the class of languages recognized by NFAs are also the same as the regular languages. Okay. So let's see some examples. Right. So one example is a set of all binary strings that end in 1, 0. Right. So one way to do that using a DFA is to keep track of the last 2 symbols that we saw. Right. So we have 4 states, q 0 0 1 0 0 1 1 1, and the accepting state is 1 0. So where you keep track of the last 2 symbols. So for instance, if the last 2 symbols that you saw was 0 0, and if you see a 1, right? If you see a 1, then this 0 becomes the penultimate symbol seen, and the last symbol that you saw would be a 1. If you see a 0, basically it's a self loop. From 0 1, if you see a 1, it is like a basically you've seen 2 1s at the end, right? If you see a 1 here, it's a self loop, and if you see a 0 from here, basically it's like, no, sorry, if you see a 0 from here, it's like this, right? And if you see a 0 from here, it's like again the state 0 from Q11, meaning the last 2 symbols that you saw was 1 1. If the next symbol is 0, so it's like 1 1 0, so the last 2 symbols are 1 0. And finally over here, if the last symbol that you saw was a 0, you go back to Q0, and if the last symbol that you see is a 1, you come to 0 1. So it's like 1 0 1, so which means the last 2 symbols is 0 1. So this is one way to keep track of the last 2 symbols, and this accepts all the strings which end in 1 0, right? In fact, this is not the smallest DFA. This is just simpler to describe. In fact, you can do something slightly smarter. You can combine these 2 states. You can combine these 2 states, I think, and basically you can get a 3-state DFA. But an NFA turns out to be really easy, which is what I wanted to say. Basically, you want the last 2 symbols to be 1 0. So you transition when you see a 1, you transition when you see a 0. You don't put any other options for Q2 and Q3. The only other option that you give is for Q1. You have a self loop when you are at Q1. So the only way to end at Q3 and get accepted, if you notice, is to remain stuck at Q1 till you see the last 2 symbols, right? So the way to accept this string 0 0 1 1 0 is to 0 you remain at Q1, 0 you remain at Q1, 1 right? So 1 you remain at Q1. The fourth symbol 1, you move to Q2, and the final symbol 0 you move to Q3, right? So suppose so this is the way to end at Q3. Suppose you move to Q2 in the third symbol 1, then you cannot proceed. This is not a valid computation path because you are at Q2 and then you have another one coming. Then you don't know what to do next. So just to give another example, suppose the string was right 0 0 1 1 0 1 0. Now suppose you 0 0 1 you remain at Q1, right? 0 0 1. The fourth symbol 1 you move to Q2, and the fifth symbol 0 you move to Q3. Now again you are stuck because there are 2 more symbols, but there is no outgoing arrow out of Q3, right? So the only way to end at Q3 in a valid legal way is to move to Q2 in the penultimate symbol and move to Q3 in the last symbol. Because if you come here early and then there are no more options available, that means it's not a valid computation. You have to read all the symbols, right? If you read part of the string and end at an accepting state, but there are strings, the part of the strings remaining, that is not a valid computation. You have to read the entire string and end at an accepting state, right? So the way to accept this string right now is for all the red symbols you remain at Q1. The sixth symbol 1 you move to Q2, and the last symbol 0 you move to Q3, right? So you see that this is an NFA and this seems to be rather simple, right? Finally, another NFA example is we want to accept all the let's say again binary alphabet. You want to accept all the strings where the third last symbol is a 1. Okay. Again, the way to do it is you remain stuck at the first state, right? And you should be able to move from Q1 to Q2 to Q3 to Q4 over the last 3 symbols. The last 3 symbols should take you to Q4, and you want to ensure that the third last symbol is a 1. So the third last transition Q1 to Q2 should happen on a 1. The second last symbol, you don't care, it could be 0 or 1, and the last symbol also, it's okay to be 0 or 1. So now the only way to end the processing of the string in a valid way is to start making these transitions Q1 to Q2, Q2 to Q3 and Q3 to Q4 over the last 3 symbols of the string. But then if you have to make these transitions over the last 3 symbols, so some kind of, let's say, some x, let's say 0, 1, 0, you cannot, this is not valid because this 0 has to take you from Q1 to Q2, but then that is not allowed. The only thing that can take you from Q1 to Q2 is a 1. So this will not be accepted, right? So this will be accepted because this one, the underlined 1, will take you from Q1 to Q2. The next one will take, the next 2 symbols will take you from Q2 to Q3 and Q3 to Q4. So if you read the book, this question is there in the CIPSER textbook. There is also a DFA that is illustrated, and this DFA has 8 states, and that is the smallest DFA that can recognize the same language, right? So you read the book, please read the book to see the DFA, and that will perhaps make you appreciate the fact that NFA is like very simple, very easy to understand. Only like you can just see it's almost a straight line except for the self loop. The DFA has 8 states with all kinds of transitions going across, right? Something similar to this idea but extended to 8 states, because you have to keep track of all the last 3 symbols that you saw, right? So this has 8 states and you cannot simplify it further, right? So you have a look. And finally, I have one more language which is a unary language. Unary means it's a language over only one symbol. So in this case, the symbol is 0. So I accept which means any string is entirely composed of zeros, and I accept the string if the length of the string. So the only parameter is the length, right? Because all the symbols are zeros. I accept the string if the length is a multiple of 2 or 3. Again, you can make DFA for it. It's not that hard, but the NFA is really simple. I'm not bothering to explain, but you can have a look. So just to summarize, we saw what is an NFA in a high level, in an informal sense. We didn't formally define it yet, and we saw examples of what gets accepted, what does not get accepted. So now we know the rules, or even though not formally so, at least we know the rules in an informal sense. We understand the rules. So the next thing to do is to define the NFA formally, which we will do in the next lecture video.